Yes, good morning, my dear students, and welcome to electronics online classes. Look here in the last class, we are discussing about the applications of your operation amplifier. As we know, why the op-amp is called operation amplifier? Because as we know, it will do the mathematical operations such as addition, subtraction, integration, differentiation, and logarithmic and anti-logarithmic amplifier. And actually, as I said in the last class, in op-amp, application can divide in two ways. One is linear applications, another is called non-linear applications. And in the last class, we have completed the linear applications. In linear applications, as we know, the output and input are direct proportional. The linear applications of but output and input are direct proportional. And in the last class, we have already discussed about different linear applications. It may be op-amp is used as inverting amplifier, or op-amp is used as non-inverting amplifier, or op-amp is used as a adder and subtractor. This much you studied in the last class. And maybe today's class, the lecture number 7. And today onwards you start the non-linear application. We'll start the non-linear applications. And as I said already, in non-linear applications, the output and input are not direct proportional. The output and input are not direct proportional. And as I said in the beginning classes, the op-amp is called, it is also important versatile integrated circuit. It is so important versatile integrated circuit. It means in op-amp you can externally add the resistors, capacitor or diodes. And how you are adding the resistor, capacitor and diode? It may be the input side and the output side. You are having the different applications of your op-amp. And especially in your inverting amplifier, non-inverting amplifier, or it may be your adder and subtractor, you are using only the resistors. Maybe in the input side or maybe in the output side, you are using only the resistors. That's why they are called linear applications. It may be inverting amplifier, non-inverting amplifier, op-amp is used as adder or op-amp is as subtractor. In all the four important applications, you are only use the resistor. Maybe in the input side or maybe in the output side. And today we'll go for the non-linear applications. In non-linear application, we are studying about the four important applications. One is called op-amp is used as a differentiator, and also the op-amp is used as a integrated. And if possible, you go for the op-amp is used as a logarithmic amplifier, and also op-amp is used as anti-logarithmic amplifier. These are the non-linear applications. And as I said, why these are called non-linear applications? Because you are not only using the resistor, also you are using capacitor and also using the diodes. And where you are using the capacitor, it may be input side or it may be the output side. We have done the classification applications of your op-amp. If your capacitor is input side, that is something but your op-amp is used as a differentiator. The same capacitor, if you connect to the output side, that is something but the integrator. And in the same way, for your op-amp, if you connect the diode in the output side, that is nothing but the logarithmic amplifier. If you connect the diode in the input side, that is nothing but anti-logarithmic amplifier. It means, as I said, you can externally connect the capacitor and diodes to your op-amp. And depending upon where you have connected the capacitor or diode, it may be the input side, it may be the output side, you have done the different types of application. Now we'll go for the op-amp is used as a op-amp is used as a differentiator. Op-amp is used as a differentiator. And as I said in the beginning, your what is the use of the operational amplifier? Especially your operational amplifier, they are using in your analog computers. They are using in your analog computers to go for the addition, subtraction, multiplication, difference, integration. They are using your op amps. It means by using the op amp, you can go for the differentiation of the signals, or you can go for the integration of the signals. And what is called op amp is used as differentiator. What is differentiator? What is differentiator? As we know, it is a circuit, but in this circuit, the output voltage is proportional to the differentiation of the input voltage, or the output voltage is proportional to the derivative of the input voltage. What I am saying? The differentiator, it is a circuit. In this circuit, the output voltage is proportional to the derivative of the input voltage. Or another important thing, what is the function of your differentiator? Means the differentiator is nothing but it will do the output voltage is proportional to the rate of change of input voltage. In differentiator, the output voltage is proportional to the rate of change of input voltage. That is nothing but the differentiator. And once again, we go for the derivations. As I said already, in this chapter there are so many derivations, and especially we are going for nearly about 8 derivations. Already we have completed 4 derivations. It may be inverting amplifier, or it may be non-inverting amplifier, or your adder and substrate we have completed. Today we go for the 2 important derivations. How actually your op amp is used as a differentiator. Basically I said in theoretically, but we want proof for mathematically can proof for that. That you go for that mathematical proof for the how your op amp is used as a differentiator. And as I said, the differentiator nothing but it is in circuit. In this circuit, the output voltage is proportional to the derivative of the input voltage, or the output voltage is proportional to the differentiation of the input voltage. And as we know, here we are using an important thing about first to draw the lead diagram, and already you have studied about in inverting and non-inverting amplifier. It is as similar to the inverting amplifier. It is as similar to the inverting amplifier, but only thing the difference is about in your inverting amplifier, we are connecting the input to the inverting terminal. It means you are using a resistance in the input side. But here everything is same as your inverting amplifier. Only in place of resistor, we are using a capacitor in the input side. The remaining as it is similar to your inverting amplifier. And now make it the non-inverting terminal ground. And as I said, it is as similar to your inverting amplifier. Take the RF, that is your feedback resistor, and here you can measure the output. And here, as I said, you are applying a capacitor in the input side. You are applying a input to the you are applying the input to the capacitor, and this is your RF, and this is your IN, IF, and IB as well, and this is nothing but your positive VCC and negative VE. As I said, you people only the change. Everything is similar to the inverting amplifier. Only in place of resistor connecting a capacitor in input side. That is nothing but the differentiator circuit. It means you are applying the input to the capacitor. And as usual, you are using a feedback resistor because always current flow through the feedback resistors, and you make it non-inverting terminal ground. And first you draw the lead diagram, and you will write where you apply the input, and this way I said you are applying input to the inverting terminal and make it non-inverting and grounded, and you are using a feedback resistor, and through the capacitor you are applying the input signal, and you are applying the biasing voltage positive AC or negative AC as usual. And now we will go for the derivation. And for the derivation, as we know how you have done in your inverting amplifier, non-inverting amplifier, adder and subtractor, same procedure can go for. And the important thing, you are using a capacitor. In the before you are using only the resistors, but in the resistor it is very simple to how your current flow in the resistor. But in capacitor there is some doubt how actually in the capacitor the current will flow. For that maybe you already studied in basics. This is your capacitor. What is capacitor? The two conducting plates separated by dielectric medium, and this is another capacitor. And in this capacitor, the important thing is about the most important property capacitor. It blocks the DC turnover phase. And actually, we want to, as the property of capacitor, in capacitor, charge is directly proportional to the voltage. In capacitor, the charge is directly proportional to the voltage. Or you can write Q is equal to C into V. Q is equal to C into V. Or you can write C is equal to Q by V. You actually want this important relation. You want this important relation. It means in this, as usual, you apply the KCL to the input side, or can say this your node A and this node B, or can write VA and VB. Apply as usual, apply KCL at node A. As usual, same. The IN equal to IB plus IF. As we know, the incoming current is equal to the outgoing current. According to our KCL, write IN equal to IB plus IF. IB plus IF. And as usual, we know that IB is 0. Why IB is 0? Because you are consider the ideal op-amp. In ideal op-amp, the input resistance is infinity. The input impedance is infinity. That's why IB is 0. It means you can write IN equal to IF. This is so important. Which you can consider equation number 1. And as usual, we want IN. And IN nothing but now you are considering the capacitor. How much the current flowing in the capacitor. And as you know, the capacitor, the current nothing but dq by dt. dq by dt. And it is as similar VA minus V0 divided by RF. In the output side, you want this current flowing through the feedback resistor. VA minus V0 divided by RF. That is very simple. You can write VA minus V0 by RF. And here we can write in place of Q, what you can write? We can write C into V. According to this equation, you can write in place of Q, we can write C into V. And we can write d by dt into C into V. This is as usual, and here VA is 0. Why VA is 0? Because of virtual ground concept. Because of virtual ground, VA, VB equal to 0. Because virtual ground. As we know already, you already started in detail. And here we get minus V0 by RF. Minus V0 by RF. Then now you take C common. It is C is constant. You take outside. It becomes C into d by dt of V. And here the V nothing but you can write VI because we are applying the input to the capacitor. VI. That is nothing but VI minus VA. Here in place of V, what you can write? Vi minus Va. Can write here. The next step, C by, I can write V only. D by dt. In place of V, we can write Vi minus Va equal to, as usual, minus V naught by Rf. Minus V naught by Rf. And in the next step, what I will do? Here also substitute the Va value 0 because of the virtual not concept. We will get C d by dt of Vi, because as I said your Va is 0. Va is 0, and here you can write as usual minus V naught by Rf. Minus V naught by Rf. Then what you want? Actually, you want the output voltage. We want the output voltage. It means this Rf will multiply here. It becomes V naught equal to minus Rf C into d by dt of V. Beta, only we done to take Rf this side. Rf into C d by dt Vi as it is. And especially this Rf and C are constant. We will get the output voltage is directly equal to the differentiation of the input voltage. That is nothing but your small direction. Actually, so many times this question asks for 5 marks. So many times this question asks for the 5 marks. And explain the op-amp is used as a differentiator. It means first you have to write what is differentiator. As I said, the differentiator, it is a circuit. In this circuit, the output voltage is proportional to the derivative of the input voltage or differentiation of the input voltage, or another I said about the main function of your differentiator is nothing but the output voltage is proportional to the rate of change of input voltage. Divided by nothing but rate of change of input voltage. And as usual, first you draw the V diagram, and here we are considering it is nothing but it is as similar to inverting amplifier. Only increase of the resistor using the capacitor. The remaining non-negative terminal noted, and you are in feedback resistor, and you are applying input to the through the capacitor. And because you are using capacitor, that's what is called a non-linear application. And as usual, we know in the capacitor the charge is direct proportional voltage, or you can write Q is equal to C into V. We want this Q value. That's why I said about this. And as usual, in your op-amp, you are using the virtual mode concept, that is VA equal to 0 because of virtual mode concept. And in the first step, what you will do, apply the KCL for the input side, or at node A, I in equal to IB plus IF, I in equal to IB plus IF, and as usual, IB is 0, as usual IB is 0, why IB is 0? Because of input impedance is infinity. IB 0, it means IN is equal to IF. And in place of IN, what you can write? Because we are using a capacitor here, you can write dq by dt. And as we know the d by dt as it is, you are going to substitute the q value. The q value is nothing but C into V. And here, it is as similar to your inverting non-inverting amplifier. We want the feedback current, that is Va minus V naught divided by Rf. It is very simple. And as usual, the Va 0 because virtual one, it will get minus V naught by Rf. And in place of Q, you can write C into V, and C is constant you take outside, d by dt of V. And in place of V, what you can write, because you are applying the input side, you are applying the input to the capacitor. That's why Vi minus Va. In place of V, we can write In place of V, we can write minus V naught by RF. In place of V, we can write VI minus VA. C divided as it is, and as usual, VA is 0, and we get C into divided of VI. This is equal to minus V naught by RF, and we want the output voltage. That's why you take RF this side, RF into C divided of VI. And finally, this RF and C are constant. Take the output voltage is proportional to the derivative of the input voltage, or the output voltage is proportional to the difference of input voltage. This is nothing but very simple derivation about the op-amp is used as a differentiator. And as I said, it is very simple, and in 1 or 2 times this question asks for 5 marks. And actually, what is the applications where you are using the differentiator? And the important thing, it is used in your wave shaping circuits. The differentiated circuit is used in your wave shaping circuits, and also it is used in, as I said in the beginning, analog converters. Your differentiator is useful, or the application differentiator is used as a in your wave shaping. Also, it is used in your analog converters. This is about the differentiator. And another important thing, the proper functioning of the differentiator or condition is there. That condition is nothing but the RC, the time constant RC is less than 10 times the T. For proper functioning of the differentiator, the RC nothing but time constant is less than the 10 times the time period. This is the one condition of your differentiator. And actually, as we know in your mathematics, what is the differentiation of sine wave? That is nothing but cos wave. Here also we can go for the op-amp can be used as a differentiator. And in what way it is used as a differentiator? Means here in the input side, if you are applying the sine wave, you will get the, in the output you will get the cos wave. If not, you can not, maybe you have followed everything. I will commit and next you go for the remaining things. It means if in the input, your input and output, if your input is sine wave, you get the inverted cos, you get the inverted cos. And why inverted? Because we are having the minus n here, we are having the minus n here, that's why it is inverted. And in the same way we go for the square wave. In the input you are having the square wave, then you go to the slice in the output, and finally you go for the triangular. Then you get the square wave as output. It means in your differentiator, in the input side, if you are applying the sine signal, sine wave signal, in the output you get the inverted cos. But in the input side, if you are applying the square wave, then you get the, in the output you get the slice. And if you are applying the triangular wave in the input side, you get the output square wave. This is about the how actually your differentiator, your op-amp is used as a differentiator. Maybe you have followed. We will go for the next one. That is also simple. That is something but your integrator. Now we go for the very small change between the integrator and differentiator. As I said in the beginning, only while connecting the capacitor, if you connect the capacitor in the input side, that is differentiator. If you connect the capacitor in the output side, that is nothing but integrator. Now we go for the op-amp. Op-amp is used as an integrator. is used as a, and once again same, what is integrator? The integrator nothing but, as I said, it is also used in analog computers, it is also used in shaping circuits. And integrator nothing but, it is also circuit. In this circuit, the output voltage is proportional to the integration of the input voltage. Or in the integrator, the output signal is proportional to the integral of the input signal. Integral of the input signal. Or you can say the integrator, it is a circuit. In this circuit, the output voltage is proportional to the integral of the input voltage. How in your differentiator, the output voltage is proportional to the differentiation of the input voltage. In the same way, for integrator, the output voltage is proportional to the integral of the input voltage or integration of the input voltage. That is something about the integrator. And as I said, very small change here, remaining as it is similar to the your differentiator. Only the change. Here we are connecting the remaining as similar to the your here you can connect the capacitor to the output side. Remaining similar to the your differentiator. And here you can apply the input. This is nothing but Ri, and this is nothing but your CF, this is IF, and IN, and IB, and this is nothing but VA, and VB. As visible, here in your integrator, you are connecting the capacitor output side. And if you are connecting the capacitor input side, that is nothing but integrator. Sorry, differentiator. If you connect the capacitor output side, that becomes the integrator. It means, as I said already, where you are connecting the capacitor, you have done the different applications of your op-amp. If you are connecting in the input side, your op-amp is used as a differentiator. If you are connecting the capacitor in the output side, that is used as a integrator. Now, as usual, you are connecting the input to the inverting terminal through the Ri, and you are connecting the, in place of feedback resistor, connecting the capacitor. Always in your inverting, non-inverting, or had a subtractor, here you are connecting in feedback resistor. In place of feedback resistor, you are connecting a capacitor, remaining as similar to your inverting amplifier. Only thing, in place of feedback resistor, you are using a capacitor in the feedback path. And as usual, the VA and VB same. Here also you are using a capacitor in the output side. That's why the Q is directly proportional to the voltage, or you can write Q is equal to C into V, and VA, VB is 0 because of virtual ground concept. Because of virtual ground, and as usual, you apply the KCL for the input side. You apply the KCL for the input side. Apply the KCL for the input side. Apply KCL at node A. That becomes, as usual, in your inverting, non-inverting, you are on the same relation. In equal to IB plus IF, and in, as usual, IB is 0 because as we know, because of Zeta is infinity, and here can write about in equal to IF, and here very simple, because you are using the input side as usual, Vi minus Va by Ri. How we got an inverting and non-inverting amplifier? Vi minus Va by Ri. In place of I, what you can write? Vi minus Va by Ri. And as usual, in the IF, you are using a capacitor. That's why I can write over dq by dt. dq by dt. And here also the Va is 0 because of your virtual load concept. That becomes Vi by Ri. This is equal to, you can write d by dt of C into E. And here you can take C constant, take outside. Vi by Ri equal to C into d by dt of V. And as usual, your capacitor in the output side. Capacitor in the output side. We can write in place of V, what you can write? V nothing but Va minus V naught. In place of V, what you can write? Va minus V naught. Can continue here. Vi here. Continue here. Vi Ri equal to C into d by dt of, in place of V, what you can write? Va minus V naught. Va minus V naught. And as usual, Va is 0 because of virtual load concept. Vi by Ri is equal to C into d by dt of minus V naught. The important thing, minus V naught. And as usual, this C divides here. Write Vi by Ri C equal to minus d by dt of. Actually, we want this V naught. And how to get the V naught? Integrate on both sides. Integrate on both sides. Integrate on both sides. Integrate on both sides. That becomes what you can write? Vi by Ri dt. Integration of minus d by dt of V naught. And as usual, as you know, the differentiation and integration, they are opposite process. They will cancel. Differentiation and integration, they will be cancelled because they are in opposite process. You get V naught equal to minus Ric into differentiation Vi and dt. This is nothing but simple way of your integration. It means here you can write finally the V naught is direct equal to the integration of Vi dt. This is nothing but the simple derivation of your integrator. And maybe you are forward here. 1 second right there. If not, I'll write 1 second. Once you write in the above portion, it's only 5 minutes. Very simple. So write apply KCL at node A. It becomes I equal to IB plus IF, and as usual IB 0 because of Zi is infinity, and can write I in equal to I out. And as usual in the I in, you are applying only the resistance. You are not having any problem. Vi minus Va by Ri. You can write Vi minus Va by Ri. And here in place of you can write dq by dt. Right? dq by dt. And here Va is 0, Vi by Ri. And here in place of q we can write d by dt of C into V. And once again Vi by Ri as it is, and you take C in the outside because it is constant, d by dt of V. And as I said, we are applying the capacitor output. We want this output voltage means Va minus V naught. You can write Vi by Ri equal to C into d by dt of Va minus V naught. And as usual, the Va is 0, it becomes Vi by Ri equal to C into d by dt of minus V naught, because Va is 0 minus as it is. Then you can this C divides here, Vi by Ric equal to minus d by dt of V. Or you can take minus on this side, Vi by Ric into d by dt of V. Now you have to remove d by dt. That's why integrate on both sides. Integrate on both sides. That becomes minus sign on the outside. Vi by Ric equal to integration of d by dt into V. Or right here also dt. And here you take Vi by Ric constant, you take outside 1 by Ric integration of Vi into dt. And as usual, this difference integration cancel, that becomes V naught. Or you can write in the finally the V naught is proportional to the V naught equal to minus Ric into integration of Vi dt. Or you can write finally, as I said, the output voltage is proportional to the integration of integration. This is nothing but your integrator. Very simple, only the thing. But remember the capacitor. Where you are connecting the capacitor. If you are connecting in the capacitor, the input side, that is differentiator. If you are connecting in the capacitor, the output side, that is integrator. Remaining as usual, it is same. And as usual, I in is equal to IF. Because you are applying KCL and IV0, IN, you can write VF minus VA by IF, you can write dq by dt, VI by RI, VA is 0, d by dt of, you can write C into V, C you take outside, d by dt as it is, this VI by RI, VI by RI as it is, C you take outside, d by dt, VA minus V naught, because here VA minus V naught, and here V by VA is 0 because virtual one. That because Vi by Ri is C into d by dt minus V naught, or you can write d by dt V naught is equal to Vi by Ric, or you take minus on this side, Vi by Ric, and finally the d by dt V naught, and we want this output voltage, and we have to remove this d by dt. That's why integrate on both sides. Vi by Ric into dt is equal to d by dt V naught, and the integration difference here both will cancel, they are opposite process. Ric equal to Vi by dt is equal for V naught, or V naught is equal to minus RS by VI dt. This is about the simple way of your integrator, how your op-amp is used as an integrator. And as usual, the important thing is about where you are using the integrators. Another thing I said, maybe the differentiator can be used in your high pass filters, but integrator can be used in your low pass filters, because here you are having the resistor in the input side. It is called low pass filter. If the capacity is the input side, that becomes high pass filter. The integrator is used in the wave shaping, it is used in the analog converters, also it is used as a low pass filter. Differentiator, it is used as high pass filter, it is used as wave shaping, also it is used as a analog converters. And here also, for the proper functioning of the integrator, the RC, the time constant is more than the 10 times the time frame. And as usual, as we know, in your input output, if you apply the input as a sine, we get the cos in output. In the integrator, if you apply the sine, we get the output cos, and if you apply the square in the input, if you apply square, you get the triangle. This is about the importance about your where you are using the, what is the main applications, and how actually your op-amp is used as a integrator and differentiator. Most important thing, in the input side, if you are applying the sine, we will get the output is cos. If you are applying the input as square wave, we will get the output is triangular wave. It means the output is integral of the input. The output voltage is signal is integral of the input. Here also output voltage and signal is integral of the input. It means if you are applying the input sine wave, in the output you get the cos, because as you know, the integration sign is minus cos. And why you are getting minus here? Because as usual, you are in the, here also you are having the minus sign, here also you are having the minus sign. But important thing, minus into minus will get the plus. As we know, the differentiation, integration of sign is minus cos. Minus cos is minus, that's why you get the cos. But in the differentiation, inverted cos, now it is only cos. But in the input square wave, we will get the output triangle. This is about how your op-amp is used as a integrator, and also it is used as a differentiator. In the next class, you go for the how actually your op-amp can be used as a logarithmic amplifier, and also it is used as a anti-logarithmic amplifier. This is about today's class. Thank you.